Graphical truss analysis of the truss joints in the aerospace structures. Introduction to the aerospace truss structure. The aerospace truss structure are the fundamental to the aircraft and the spacecraft, designed providing expectational strength to the weight ratios. Their integrity is the permute for the flight safety and the mission successful. This structure, the composed to the interconnected members, bear significant load. Understanding the stress distribution with their joints critical to the prevent the catastrophic failure, ensuring the longevity and the reliability of the aircraft vehicles. Fundamental stress distribution in the stress joints. Axial force, the member primarily experience the tensile or the compressive force along their axis, determining the base, the stress statement. The load paths. Force are the transferred through the joint, disturbing the stress, the connectrically or the unevenly, depending on geometry. Basically depends on geometry. The stress uh, concentration, the sharp corners, holes, or abrupt changes in the cross-sectional leads to the localized the stress the stress spikes, a critical area for the analysis. Traditional analytical versus graphical analysis. The traditional analytical method and the graphical stress analysis. Mathematical equation are the formulas, and the formulas the sustainable simply idealized the geometry can be time consuming for the complex systems. Results are the numerical, require the interpretation. Graphical trace analysis, the visual representation of the truss field. Second one, the ideal for the complex irregular joints, the geometrics, provide the individual in the sites into the stress flow, the facilitate the rapid identification of the critical zones. Advanced visualization techniques for the complex stress patterns. The stress heat maps, the color coded maps, they visually represent the stress intensity, highlighting high stress area, the vibrate hues. Isolin controls, the line connecting point to the equal trace, the similar to the topographic maps, offer the precise stress gradient visualization. The vector, the aerodynamics direction and the magnetic of the principal stresses, the revealing the stress flow, the potential failure paths. The 3D uh, renderings, the intervacative, the models allow the engineers to they explore the stress distribution from the multiple angles, the enhancing the compressions. Case study, the stress concentration in the aircraft wings, the stress connections. The initial analysis showed the uniform stress distribution, but the graphical method revolved the localized hot spots of the fasters holes due to the manufacturing tolerance. Second one, the design modification informed by the visual truss. The pattern included reprofiling edges and the increasing matter thickness in the specific region, reducing peak stress by the 25%. Uh, Third one, the lead. The lead to a 15% increase the fatigue life and enhanced the overall the structural integrity. The validate through the sub, sub, subsequent physical testings by the airplane. Now, computational tools for the graphical trace and analysis. The modern software they leverage the computational force computational power to the generate the so sophisticated graphical trust analysis, integrating the seamlessly with the CAD and FEA. Uh, this tool enhanced the rapid uh, iteration, the allowing engineer to the quick test design change and the visualize the impact of the stress distribution, the significant accelerating and the design cycles for the aerospace aircrafts. Materials consideration and their impact on the joint truss stress distribution. First one, the material properties. Elastic modules yield strength and the position ratio of the directly influence how stress is the distributed and the observed with the joints. Second one, anisotropy. The composite, the material, the common is the aerospace exhibit the directional depends the properties, the requiring the specialized graphical techniques to prevent the stress accurately. Third one, temperature effect. The thermal expansion and the concentrating can be induced the additional stress, the especially environment with the extreme temperature variations. Fourth one, aging and the fating. The over time the material degradation and the fatigue can be altered the stress and the distribution of the increasing the sustainability failure under the repeated loading. Failure prediction and the prevention through the visual stress mapping. First, by the visual identification test, the hot spotted that the proximity to the material limit, the engineer can be predict the potential crack, the initial points. The graphical mapping uh, aids into the optimizing the joints, the geometry and the material section. It the mitigates this the risk enhancing the components durability. Third, it is also informing strategy placement of the sensor for the real time, the monitoring, creating and early warming system in the services, the components. Implementation and the strategies and the future researching direction. Integrating early design, they incorporate graphical stress analysis from the initial design, the phases to optimize the geometry and the material use. AI drives analysis utilize AI machine learning and the predict the optimized joints, design and analysis the complex stress and the behavior automatically. Real-time monitoring, the develop the system with the connect the real-time graphical stress mapping in the ensure the aerospace structures. Fourth one, the material innovation. The research can be materials and the additive the manufacturing techniques, analyzing their unique stress and the responsive the visualize. Thank you.